I recently programmed a little MIDI player for fun, and in this video I will share with you everything I've learned about MIDI. The first thing to know about MIDI data is that it doesn't contain any audio. So you may be wondering, where are the sounds coming from? In my software they come from a separate kind of file called a sound font, but they could also be generated by dedicated hardware like a synthesizer. Sound fonts provide sample data that we can use for instruments. Of course, we can play the same music back with different sound fonts. Here, the Final Fantasy VII battle theme you're hearing has that iconic MIDI sound. But I can easily replace the sound font with this chiptune one. Now, in this video, we're going to focus exclusively on MIDI, but the next video on this channel will be all about sound fonts, so stay tuned if you're interested in them. Anyway, what exactly is MIDI? It's a standard for how devices, usually musical devices, communicate with one another. If you connect an instrument like a keyboard to your computer, it may use MIDI to communicate. What's important to note, again, is that MIDI does not involve actual sound. Instead, it uses events to communicate what happened to a device. In a MIDI file, we're storing these events for a later time as a file on your computer. Here's a simplified example of what an event may look like. First, the event has a type, which tells us exactly what happened. This could be a note being pressed, a note being released, controls being used, tempo changes, and so on. And then the event has a delta time. This tells us how much time has passed since the previous event. If the delta time is 0, two events can occur at the same time. Events also have some additional data to tell us more about what exactly happened, but we'll ignore that for the moment. Now, we don't just have a single event, of course, we have multiple, and they're stored in big lists called tracks. So a MIDI file is just a collection of tracks which contain events. This event you see right here is a note on event. It indicates that, for example, a key on a keyboard has been pressed. This next event is a note off event. It tells us that the key was released. And this is how MIDI tracks store music. There are simply a ton of events that record what happened to an instrument. So far so good, but if we have MIDI data in a file, how exactly is this file structured? Like any file on your computer, a MIDI file is just made up of binary data, which is a pile of numbers that have some sort of meaning. So let's make some sense of them. First, our MIDI file is split into chunks. Each chunk has a label, followed by a size, and then the actual data of the chunk. The entire MIDI file is simply a list of these chunks, one after another. The first chunk is always a special header. Here's what it looks like as plain bytes. The first 4 bytes store the chunk's label. If we decode this label using the ASCII encoding, we can see that it just spells MTHD. This indicates the MIDI header. Next, we have 4 bytes storing the size of the chunk's data. Note that this is stored in big endian, so the most significant byte comes first, and then follows the actual data of the header, which are the 6 bytes we were just told about. They represent 3 separate values, each taking up 2 bytes. The first stores the format of our file. The format has 3 possible values: format 0, format 1, or format 2. Format 0 indicates that the file contains a header followed by a single track. Format 1 indicates that the file contains the header followed by multiple tracks. And as far as I understand, format 2 is basically the same as format 1, except that each track represents a pattern. The thing is, I have yet to encounter a MIDI file that uses format 2, so I'm not really sure how it works. The next 2 bytes tell us how many tracks are in the MIDI file. And finally, the last 2 bytes represent the number of divisions. Remember delta times? They're stored in a unit called a tick. But what's the duration of a tick? That's what the divisions value is for. What makes it a little odd is that it can be represented in 2 different ways. The most significant bit of this value tells us whether we're using something called SMPTE time. In our case, the bit is 0, which means we are not using it. That means we simply read the remaining bits, and they tell us how many ticks are in a quarter note. Why quarter notes? Well, we'll talk about that a little bit later when we talk about timing, but we can use this value to figure out how long a tick is. However, if the most significant bit is a 1, which of course it isn't in this example, but let's just pretend, then the next 7 bits store a negative frame rate in 2's complement. For example, negative 30 FPS. Why is it negative? I have absolutely no idea. Maybe someone can tell us in the comments. The remaining byte stores the resolution of a frame. Again, all MIDI files I've found use ticks per quarter note. So maybe the SMPTE timecode thing is mostly used in real-time communication of devices? I have no idea. So I did not implement the SMPTE timecode variant, and we're going to ignore it in this video. However, if you're interested in it, the Wikipedia page titled MIDI timecode has some additional info on the subject. And that's all for the divisions value. We'll get back to it in a little bit. Following the header chunk, each track gets its own chunk as well. These chunks have a label with the ASCII characters MTRK, indicating a MIDI track. The size is again a big endian value, representing the number of data bytes following. The data itself is a little more ambiguous this time. For this example, we know it's exactly 8 bytes long, but what do these 8 bytes represent? It turns out the data is just an array of events. But we don't know in advance how many events there are, so we need to read them one by one. Every event begins with a delta time. Remember, this is just the amount of time that has passed since the previous event. For our first event, that's a 0, meaning it happens immediately. Following the delta time is the event status. This byte represents the type of event that occurred, and sometimes some additional info. In this case, we have 90 in hexadecimal. The first nibble, 9, means that this is a note on event, so a key on our keyboard has been pressed. The second nibble, 0, indicates that this note is played on the MIDI channel at index 0. These indices start at 0, but when people talk about MIDI channels, they start at 1. What the next byte represents depends on the kind of event we're dealing with. For a note on event, the next byte indicates which note was pressed. Here, 3C. How do we know what number corresponds to what note? For that, we have a handy little table. As you can see, note values start at 0 and increment all the way to 127. So only 7 bits are used. If we wanted to play an F sharp in octave 3, as we can see in this table, that would be a note value of 54 in decimal. Now in our event, the note was 3C, which is 60 in decimal. Looking it up in this table, we can see that it is a C on octave 4, also called middle C. Back to our event, the next byte represents the velocity of our note being pressed. This value tells us how hard the key was pressed, as a range between 0 and 127. 127 means as hard as possible. Anyway, that's it for the first event. We saw that the note on event had a delta time, status, and 2 additional data bytes. As there are still bytes left, however, another event must be following. Again, we begin by reading the delta time. It is 0C, so that means 12 ticks have passed. The status is 80, indicating a note off event at channel index 0. And our note is middle C again, with a velocity value of 0. This makes up our second event. Now that no bytes are left, we know that all events have been read. Back to our track chunk, the whole thing would look like this. I went ahead and manually wrote a MIDI file byte by byte using a hex editor with this exact track chunk. Then I ran it through my MIDI player, which plays the MIDI file back and visualizes it. Here's the result. Let's hear it again. And there we go. It's not very impressive, but this is all there is to it. Tracks contain events, and events tell us what happens. They're just a list of bytes, each made up of a delta time, status, and related data. And by adding more events that play more notes on different channels, we can achieve results like this. You may have noticed that so far our delta times were a single byte. But what if we wanted to have a delta time larger than 255? To account for that, MIDI uses something called a variable length quantity. These values are stored using a variable number of bytes, which allows us to compress the number of bytes used. The idea is pretty simple. When reading a variable length quantity, we first read a single byte. Its leftmost bit determines whether additional bytes will follow. Here it has a value of 1, which means we have to read another byte. Let's do that. In this byte, once again, the leftmost bit is a 1. So we have to read another byte. And finally, in this one, the leftmost bit is a 0. Therefore, we have no additional bytes to read. To get our actual variable length quantity, we now get rid of the leftmost bits of each byte and shift the remaining bits together. We do this because the leftmost bits aren't actually part of our quantity, they just serve as indicators. With this approach, we can use any number of bytes to store a delta time. They don't necessarily use a single byte, they could use any number of them. At the end of the video, you'll see a code sample showing how to read variable length quantities. Another complication when parsing events is something called running status, a very simple form of compression. Here are some events that you would find inside of a track chunk. All they do is play 3 keys with slight delays, forming a chord. We have event 1, followed by event 2, and then event 3. Now let's take these events and align them row by row. Notice something inefficient here? Each of these events is a node on event on channel index 0. That means all our status bytes are identical. But what if we were to simply omit the duplicate status bytes? Now we can just keep track of the latest status, called the running status, and use it for any event that's missing a status byte. The same 3 events now use 2 less bytes. Nice. But now let's try and go back and read these events byte by byte. We start with the delta time, then get our first status, followed by the data byte for the note and another for the velocity. Fair enough, that's event 1, same as before. For event 2, we again read the delta time, but now we have a little bit of a problem. We wouldn't know if this byte is a status byte, or if the status was omitted, a data byte. So which is it? Remember how our data bytes, like the note and velocity, only use 7 of their 8 bits? Their values go from 0 to 127, so the leftmost bit is always a 0. Status bytes, on the other hand, were chosen to always be values that have their leftmost bit set to 1. So by looking at the leftmost bit of this byte, we know if it's a status or a data byte. In our case, the bit is a 0, indicating that this is a data byte, which means the status of this event was omitted. And the same goes for event 3. For both of them, we need to use the most recent status that we read, the running status, which here is the status of event 1. The whole thing is actually pretty simple, it just adds a minor annoyance that we have to account for. Again, at the end of the video, I will share a simple code snippet showing how to handle the running status. But first, let's look at the kind of events that we can find inside of our track chunks. First off are the basic events. We already saw event type 8 and 9 for the node off and node on events. Then we have polyphonic key pressure and channel pressure, which are used for a feature called aftertouch. Some keyboards allow you to press keys harder while keys were already being pressed to trigger effects and such. That's what these events are for. Control change events are used to indicate that control buttons or knobs were pressed or turned on the device. The same goes for the pitch wheel change, except it just corresponds to the pitch wheel. Finally, there are program changes. What's a program? For our purposes, each program corresponds to a different instrument. This isn't strictly true. For example, you may have a program for percussion, which contains a number of instruments in one program, but let's ignore that for now. Here's a list of all instruments defined by General MIDI, which is a subset of the MIDI standard. The Wikipedia page for General MIDI has this list if you need it. Using the program change event, we can assign different programs to our channels. Each channel may have a single program assigned at any given time. Moving on, we have more events, such as common system events. Each of these events has a length following the status, which tells us how long the event's data is. Note that this length is again a variable length quantity, meaning it isn't always a single byte. Our first system event is the system exclusive event. It lets manufacturers include custom events. The data bytes start with a 1 or 3 byte ID, followed by any number of bytes of custom data. Also worth mentioning is the timecode quarter frame event. This one is weird and wasn't explained in any of the documentation I saw, but the Wikipedia page for the MIDI timecode has a good explanation. This event seems to occur in groups of 8. For each of these events, the most significant nibble of the data byte represents what portion of the timecode the event describes. The least significant nibble then contains the value for this portion. Again, this is used when you're working with the SMPTE timecode or the MIDI timecode, so again, we're going to ignore it, but I thought it was worth mentioning. Then we also have real-time system events. These aren't that interesting to us either, as they're used during real-time communication of devices. For playing back a MIDI file, these don't really matter. Then we have meta events. First, let's talk about text-based ones. As you can see, each meta event starts with the status FF, followed by a type, and again a variable length quantity for the length of our data. The data bytes are a single string of characters with the previously defined length. These events store things like copyright notices, sequence or instrument names, or even lyrics. That's right, MIDI files may contain lyrics. Pretty cool. But there are also meta events that don't store text. Notable here are the tempo and time signature events. These are very important to determine how fast our MIDI file is being played back. Tempo is stored as a 3-byte value and represents the number of microseconds in a quarter note. The time signature, on the other hand, stores 4 separate bytes. The first 2 are a numerator and denominator, representing the top and bottom number of the time signature. Note that the denominator is actually stored as a power of 2. So if the denominator is 3, we raise 2 to the power of 3 to get 8. That's our real denominator. The third byte represents how many MIDI clocks are in a metronome click. The fourth byte represents how many 30-second notes are in a quarter note. This may seem redundant because isn't the amount of 30-second notes in a quarter note constant? Apparently not. I'm going to be honest, I don't really get why this would be a thing, but that's what the documentation says. But for a simple MIDI player, we don't really need the last 2 values. We just need the numerator and especially the denominator. I mentioned quarter notes, ticks, time signatures, and stuff like that, but how exactly do those fit together? First of all, here are some bars of music. Bars are just the separated areas you see here. They're also sometimes called measures. We can fill bars with notes. Here are 4 quarter notes in our first bar. Now, how many notes fit into a bar is determined by the time signature, here 4/4. And time signatures use a unit called a beat. The top number simply tells us how many beats fit inside of a bar, and the bottom number tells us what kind of note represents a beat. So here we have 4 beats in a bar, and each beat is represented using a quarter note. In other words, 4 quarter notes fit into a bar. Now the bar could of course contain half notes and quarter notes and whatever in any combination you want. All that matters is that the time signature tells us how much space we have and what kind of note makes up a beat. If the bottom number of our time signature was a 2, then a beat would be represented using half notes. And if it was an 8, beats would be represented using eighth notes. But for now, let's just assume that our time signature is 4/4. The speed at which we are playing back music can be defined in beats per minute. Here's some space representing a minute, and I'm going to fill this space with 120 quarter notes, which we'll assume represent a beat each. That means we have 120 beats per minute. Okay, so far so good, but where does a MIDI file store the BPM? Remember our meta events? There was one called setTempo. It tells us how many microseconds are inside of a quarter note. Using this tempo, we can easily calculate the BPM. Say our tempo is 500,000, so a quarter note has a duration of 500,000 microseconds. We take 1 million, because we have microseconds, divide that by the tempo, and we get 2 beats per second. Then multiply that by 60 and we get our beats per minute, which is 120. What if our time signature was different, for example 4/2? We're calculating our BPM using the MIDI tempo, which is the duration of a quarter note. But if our time signature was 4/2, then a beat is represented using a half note, which has twice the duration of a quarter note. To account for this, we need to multiply our BPM by 2/4. 2 because we're using half notes to represent a beat, and we divide by 4 because our tempo is in quarter notes. This effectively halves our BPM. If instead our time signature was something like 6/8 for example, then we'd multiply the BPM by 8/4. Makes sense, here each beat is half the duration of a quarter note, so the BPM doubles. And that's it for the BPM. But we need to know something else. Remember our delta times used a unit called a tick. But what's the duration of a tick? Let's go back to our MIDI header chunk. Remember this value over here called divisions? In our case, it represents how many ticks are in a quarter note. Here is a quarter note. If we pretend our divisions value is 24, that means there are 24 ticks in a single quarter note. How would we calculate how many seconds are in a tick? Well, we know from the tempo how many microseconds are in a quarter note. So if we divide the tempo by 1,000,000, we get 0.5 seconds. And if we divide that by 24 ticks, we get 0.02083 repeating. That's the duration of a tick. Knowing that this is how long a tick is, we can multiply our delta times with this value to convert them into seconds. Here's a hypothetical event. Again, the bytes represent delta time, status, which here is a note on event for channel 0, followed by the note and velocity. Our delta time is 8C, or 140 in decimal. Multiplying it by the duration of a tick, we get 2.916 repeating seconds, so almost 3 seconds. That's how much time needs to pass since the previous event for this event to occur. In most real MIDI files, the divisions value is going to be much larger than our example of 24. That's because we want to be able to get more accurate delta times. Okay, so this video is all about the format of MIDI files rather than about code. So I would like to challenge you to write your own code without any full examples. I think taking what you learned in this video and writing stuff on your own is really good practice. So maybe try and write your own MIDI parser. Or if that's too easy for you, write a parser and then take the data that you've read to create some kind of program that visualizes a MIDI file. Or maybe one that plays back synthesized audio so you can hear the music. If you absolutely need existing code bases to learn from, Google MIDI parser or MIDI player and you'll find plenty of repositories. In your language of choice too. What I do want to show you though is the basic idea behind parsing a MIDI file and how stuff like the running status or variable length quantities work. So let's at least look at some snippets of code. Let's assume we have some kind of file object and its type has methods for reading and peeking a specific number of bytes. Python, of course, which we're using for this example, has its own way of reading binary data from files, but we'll simplify things with our custom type to keep things language agnostic. And remember, our data generally uses big endian byte ordering, so let's assume the file object reads multi-byte values as such. The first thing we do is read all the header chunk's information, because it's guaranteed to be our first chunk. Next, we need to parse all track chunks. We just loop until we reach the end of the file. For each chunk, we read its identifier, size, and determine the end position of the chunk in our file. Next, we make sure that this is actually a track chunk. Custom MIDI chunks can exist, so if we find one, we'll just skip it. If we do have a track chunk, then the first thing we do is keep track of our running status. Then we loop until we reach the end of the chunk's data. Our goal is to read all the events in the track. Each event starts with a delta time, so we read that as a variable length quantity. The next byte is either a status byte or a data byte if we're using the running status. So we peek at it and use the leftmost bit to determine which of the two it is. If we have a status byte, we read it as such, otherwise we simply reuse the current running status. Note that the very first event is always guaranteed to have a status byte. Finally, we need to read the event's data. For that, let's call a function called readEvent. What does this readEvent function look like? Well, that's really up to you. The status can be used to determine what kind of event we're dealing with. At this point, you'll need to check which event the status corresponds to and read the correct number of data bytes. For example, a note on event would read 2 data bytes for the note and velocity. Once you read your event data, you can place the events in some kind of data structure of your own. But again, this part is completely up to you and the language you're using. What I do want to show you though is how to read variable length quantities. First, we define a variable to keep track of our value. Then we need a do-while loop. Python doesn't have those, so I'm going to use a while true loop with an if statement at the end. At every iteration, we read a single byte. Then we OR the 7 least significant bits of our byte into our value. Remember, the most significant bit indicates whether more bytes will follow. If it is a 1, we simply shift our value's bits to the left by 7 places to make space for the next 7 bits. Otherwise, we know that we're done and we break out of the loop. Pretty simple. You now know the most important stuff about MIDI data. For more info, I'll link the official documentation and useful links about the MIDI standard in the video description. Definitely check them out. With everything in this video, you should be able to write your own MIDI parser. However, we are not quite there if you want to fully implement a MIDI player. The big missing piece is, of course, the sound font. These files contain the sample data and a ton of information about how samples should be handled. Because they're quite complicated, we'll talk about them in the next video. But for now, thank you for watching and have a good one.